Okay, so now I think that it's time to move to the next speaker. And Leonardo, please, could you please introduce Sviatlana for the next
Yes.
talk?
Thank you, Marjorie. By the end of 2014, when I started my PhD on the use of SVET at Mons, a senior researcher in the lab gave me a USB drive full of Sviatlana Lamaka's papers. And he just said, now you have everything you need to start your PhD journey. And I remember a bit late, in 2015, I had the chance to go to my first conference in Graz. No, Graz was my second conference. It was Troia, Portugal, my first conference. And Sviatlana was there. I approached her. I explained a bit what I was doing. And she gave a very nice response. Instead of overselling her, she just said, you should read Vincent Vivier, you should read Nadine Pebert. They are doing local electrochemistry at the highest level. Then I have the chance to see her again at Graz this time, EuroCort 2015. And I still remember my reaction because I was finally mastering a bit the traditional SVET, let's say, and then she was presenting simultaneous measurements of current density, dissolved oxygen in the solution, pH. I was, oh, and she still got all of that. Okay, so she really motivated me to pursue my research at the time. So it's my personal honor to introduce one of my research heroes, I would say.
Thank you very much, Leonardo. It's really unexpected and very interesting feedback that I got from you. Yeah, you try to do your best as a researcher, being humble and digging for as deep as you can to understand the processes. And of course, it's always a pleasure to share with young scientists, same way as I was young scientist, and all the colleagues were advising me in the nicest possible way. So then thank you very much indeed for organizing this webinar within European Federation of Corrosion Working Party 14 for coatings. I will try then to share maybe some newer developments compared to those that were shared to Leonardo and other colleagues, and hope that whatever I present today might be inspiring, somehow interesting for you, and then you will continue with your own research even better than whatever I'm doing with a lot of very strong colleagues. I will then share my screen and start my talk. Again. Okay, now I think you see it, but in present mode, I will swap the screens. Can you see now my slides?
Yes, we can.
Yeah. All right, then thank you very much. Thank you for very unusual introduction, Leonardo. Thank you, Marjorie. Marta, I guess, was also involved with organizing this webinar. I lead the Department of Electrochemistry and Big Data at the Institute of Surface Science of Helmholtz-Zentrum Hereon. It's north of Germany, near Hamburg, in a smaller town called Gestacht. And today I would share with you my knowledge about probing coated metal interfaces with local electrochemical and not only electrochemical methods. Well, since you're here, you're well aware about corrosion problems and how much all this costs to all of us. And here there is an interesting diagram showing the measures that can be used to improve metal sustainability. And these measures are ranked here based on potential for impact from low to high and technology readiness from far to near. And there are a number of measures here that you would recognize: reuse of alloys, recycling-oriented alloy design, additive manufacturing, scrap sorting and separation, and corrosion protection. Corrosion protection is ranked highest among all the measures based on technology readiness and potential for impact. So indeed, we are in a good place for improving metal sustainability. And it has been estimated that implementing best practices in corrosion prevention may result in global savings of up to 35%, which is, of course, a staggering number. Well, obviously, implementing corrosion protection measures require a clear understanding of corrosion mechanisms. And scanning microprobe techniques have been proven to provide valuable information about specific steps of corrosion mechanisms in many different materials. So here I have a number of techniques that I listed, starting with scanning vibrating electrode technique, and its older brother, scanning reference electrode technique, then scanning electrochemical microscopy with using potentiometric or parametric microprobes, scanning microbe dot, which is in fact not an electrochemical sensor, but I included it here because it gives a lot of interesting information about electrochemical processes locally. The localized electrochemical impedance spectroscopy, electrochemical cell microscopy. Basically, it's a nanodroplet that hops from one location to another and can provide mapping of electrochemical activity of specific material. Electrochemical IFM, SCAP IFM, Kelvin probe, and scanning tunnel microscopy. Some of them are not, well, it's not fully correct maybe to call them electrochemical because they operate in air or controlled gas, but still they provide very valuable information about corrosion processes, and that's why they are listed here. I would like to focus on this particular set of techniques, and this is not because they are any better or worse of what is listed here. It's more that experimental setups and data interpretation for all these techniques, well, is quite tricky. Yeah, you need to have a lot of experience and hands-on experience and understand how to avoid misinterpretation, avoid pitfalls while performing the measurements. So basically, I will speak about techniques that I have used myself for some years now, and think more or less understand what to expect. And then if you want to learn more about these methods, you probably should find colleagues who have more experience with these methods. Yeah. So then before we start talking about the techniques themselves, let's maybe try to understand what exactly we are trying to catch with these local electrochemical methods. So anodic oxidation and cathodic reduction processes lead to significant changes at metal interface. We have strong ionic fluxes generated due to anodic oxidation, then hydrogen evolution due to this reduction process, and oxygen reduction, which is main cathodic process for aluminum, zinc, iron-based alloys, and secondary process for magnesium. And this, of course, also lead to evolution of gaseous hydrogen, consumption of oxygen, and local alkalinization as a result of these two cathodic processes. And anodic oxidation also leads to pH change, apart from strong ionic fluxes. And in this case, this is local acidification due to hydrolysis of ions that are formed as a consequence of anodic oxidation. And this hydrolysis might lead to rather significant acidification, depending on the stability, on the hydrolysis constant, which is related to stability constant of the hydroxide. And this acidification is especially pronounced for aluminum-based alloys and for iron-based alloys. And this what is basically driving pitting corrosion for these metals. So these are the changes that we will try to catch with the techniques that I present: local pH changes, ionic fluxes, and evolution of hydrogen and consumption of oxygen. It is also very important to understand that all the electrochemical processes, corrosion processes, they happen at metal surface, at the interface, rather than in bulk electrolyte. And that's why there is a big difference in the concentration of species if you look at bulk electrolyte and metal surface. So here I have example of approach curves, so from 1 millimeter to the metal surface. In this case, it's platinum. It's 270 micrometer disc that was embedded in epoxy. And then we injected either negative or positive current, observing oxygen reduction reaction with alkalinization in this case, or oxygen evolution process with water oxidation in case of positive polarization. And you see that as we approach from 1 millimeter height to the surface, we see significant changes of local pH. I will, of course, later on speak about microprobes that we used for this. Then another example, this is ultra high purity magnesium in sodium chloride electrolyte. And here we perform approach curves with hydrogen sensitive microprobe, oxygen sensitive microprobe, and pH. And again, we see very strong changes as we move from 2 millimeter height to metal surface. The thickness of the diffusion layer is strongly dependent on the electrolyte flow, so on fluid velocity. The stronger is the convection, the thinner is electrolyte, is a diffusion layer. Then, of course, depends on the diffusion coefficient. The higher is diffusion coefficient, the thinner is diffusion layer, electrolyte viscosity, temperature, and so on. All right, now let's move to the techniques. We start with SVET. So basically, SVET reveals net fluxes of positively and negatively charged ions. I took this very nice image from publications of Dr. Ashandra Bastos from University of Aveiro. He is probably the strongest expert in SVET methods and published very valuable, very informative reviews on this topic. And so in this work, he has galvanically connected zinc and iron electrodes embedded in epoxy, and so there is galvanic corrosion going on. And with SVET, it's really very easy to visualize this upward flux of charged zinc ions and also flux of negatively charged OH ions due to cathodic process on iron. And that's why it looks like if it's downward flux. And basically, this is what SVET is doing, measuring the net fluxes of positively and negatively charged ions. This is a typical setup with vibrating probe, and vibration piezo elements are located in this part of the vibration head, reference and ground electrodes. Typically, vibration probe is platinum iridium. We use commercial microprobes there are several suppliers for this. And then this is platinum iridium microprobe with only apex of the tip that is not insulated. And we grow the layer of platinum black. The diameter of the probe is between 10 to maybe 20 micrometers, and vibration amplitude also between 10 to 20, maybe 30 micrometers, but not more than that. And so then vibrating probe of SVET during this vibration between 2 points near metal surface measures the potential difference that is formed in solution due to the ionic fluxes produced on the sample surface due to chemical or electrochemical reaction. And then relationship between this measured potential difference and associated current density is established by calibration. So before we perform the current calibration, and this is a typical view of the calibration setup, this is a vibrating probe of SVET approached to fixed distance. Normally, it's 150 micrometers. So it is approached to point current source. In this case, it's glass capillary, and then we inject positive current of 60 nanoampere. And before we perform this current calibration, we also calibrate the geometry of the probe vibration to make sure that there is only a vertical or only horizontal, so this probe vibrates in 2 planes. And then after vibration frequency and vibration amplitude is fixed, then we perform a current calibration. And this is done based on this equation that if we drive 60 nanoampere current at this distance, we expect to reach 21.2 microamp per square centimeter current density. So basically, SVET registers outbreaks and suppression of local corrosion. This is the example of PEO-treated magnesium sample. We continue Federica's topic of PEO-treated magnesium. In this case, it's that E41 alloy treated with PEO and also loaded with corrosion inhibitors, or this is a reference sample that is unsealed also with thin sol gel film. And in this case, we made defects in this coating, and then we started SVET measurements, and we clearly see outbreaks of corrosion activity. And here we compare this reference sample with the one containing corrosion inhibitor. And by looking at the peak value of current density, we compare the activity of the sample and how it activates and then decreases with time. Apart from comparing peak values of current density, we can also integrate SVET data, and it's another way of presenting it. So this is example of galvanized steel with also artificial defect in the middle, and then we measure current density by SVET, and then we separate these two types of current, positive and negative currents, separated, and we can then integrate them to get the total current. Of course, cathodic current must be equal to anodic current in any electrochemical process. But it's not always that we are able to capture this. Yeah, there are several reasons. For example, if you work with coated samples and some cathodic activity might be undergoing under the coating, and then you're not able to visualize it properly with SVET. Or typically cathodic areas are larger, and hence total activity per surface area is somewhat lower, and SVET might also miss this. And so in reality, we see sometimes that this condition is not always true, but yeah, we typically should be able to find out the reasons for this. And this is an example of where we compared integrated anodic and cathodic currents. Again, this is galvanized steel with a number of inhibitors loaded in various carriers, and here we clearly see initial strong corrosion activity in one of these samples. In another sample, it's other way around, so there is good passivation, and then in some time there is outbreak of corrosion activity, and then combination of these containers leads to optimal performance with low corrosion currents, both anodic and cathodic. Well, SVET indeed is a very powerful method used quite widely in corrosion science, but it provides no information about ions or molecular species that contribute to the ionic fluxes or chemical reactions. And that's why, together with SVET, we use a set of other microprobes, and I will now speak about this. So we use a pH-sensitive microelectrode, hydrogen sensitive to concentration of dissolved gaseous hydrogen, and oxygen selective amperometric probe, and oxygen quenching microoptode. So we have just published a review paper where we considered advantages and disadvantages of various pH-sensitive microelectrodes, and this is the table from this recent publication. Indeed, they have all of them, so this glass electrode or oxide microprobe, or based on ionophores, pH selective electrodes, solid contact electrodes, and so on. They all have their own pros and cons, but now, having worked with all of them for some years, since I tried these commercial microprobes, and I'm not affiliated with the company in any way, I'm just sharing my user experience, but since we tried these commercial pH-sensitive microprobes from Unisense, so the tip of the microprobe is really made of pH-sensitive glass. So it's the same principle as you use for macro electrodes, for the centimeter size pH-sensitive electrode in the lab. And so really the biggest advantage of these microprobes is that the readings are exceptionally stable. Yeah, so there is a very stable potential. There is no drift of potential, and this is the most important property of the pH electrode for me, at least, because we can fully rely on the values and don't think about what might have happened, was a drift of potential, and that's what we typically observed for glass capillary microelectrodes with ion selective ionophore in the tip. They are unfortunately prone to some potential drift, and this complicates that interpretation. Now, the disadvantages of these glass electrodes are that they are still very fragile because the tip is very small. Well, small, depending, of course, on what you're comparing to, because so the diameter is around 10 micrometers, but the length is around 50 micrometers. So if you really want to do point analysis, perhaps ionophore-based microelectrodes is still an option, because here we're talking about a diameter of the orifice of 2-3 micrometers, so it's smaller tip size. But nevertheless, the biggest advantage is very, very stable potential. Now, for oxygen sensing, we use two types of microprobes. This is example of oxygen sensing microoptode. As I already mentioned, this is non-electrochemical sensor. This is essentially optic fiber with chrome ionophore mobilized at the apex of the tip. Again, this is commercial microprobe from a German company, Pyroscience. I'm not affiliated in any way. However, I did suggest this company and this type of sensors to many other colleagues, and I think they developed their own techniques by now using this. We are using Pyroscience microoptodes for over 10, 12 years. We started at the technical in Lisboa and still continue using them. So they possess very stable signal, very low detection limit, high selectivity, and they are quite affordable. These microprobes, they are temperature sensitive, which is neither advantage nor disadvantage. It's just the property that you need to take into account. Basically, any measurement with optode needs to be compensated by temperature, and this is quite easy if you use equipment from this company because it's all provided in the same package. Well, the only disadvantage here is somewhat larger tip, again, 50 to 70 micrometers. And then if you want to go for much smaller tip size, then a parametric Clark type microprobe, also sensitive to concentration of dissolved oxygen, is a very good alternative indeed. A small tip diameter from 3 to 500 micrometers you can choose for your application. These are commercial microprobes again. And very stable signal, very fast response. However, still microprobes, so these microprobes are highly fragile and very expensive. The principle is parametric probe, so there is a gold cathode inside the microprobe, and it's biased to minus 0.8 volts, so there is oxygen reduction on this gold cathode that a current is measured. Here there is a semi-permeable silicon membrane that only lets gaseous species to pass to the gold cathode. Similar to this, a parametric Clark type microprobe sensitive to concentration of dissolved hydrogen. Again, very small tip size, stable signal. The difference is that there is platinum anode inside that is biased positively, and there is a hydrogen oxidation, and the oxidation current is recorded. This is the typical cell that we use. So we have a metallic sample embedded in epoxy. This is an optical photo, and then we put electrochemical cell and approach our microprobes 20 to 50 micrometers to this surface. This is a real sample. This is actually a magnesium-made cardiovascular stent, and we perform some measurements. But for flat samples, we can combine 2 or even 3 microprobes. In this case, this is optode together with pH-sensitive microprobe scanning across this sample, and we can then get distribution of local concentration of dissolved oxygen and pH. This is a typical setup. This slide was created by Dr. Chen Wan, our PhD student, who did a lot of work with microprobes. So we always work in Faraday cage for canceling external electromagnetic fields and an anti-vibration table. Put this sample on a movable sample holder with light source and the camera. So we always capture visual appearance of the sample at any moment of measurement. We provide medium with peristaltic pump, and this can be either sodium chloride or if you work with metallic implants and HPSS, so other simulated body fluids, electrolytes. And we can work either at room temperature or in thermostated cells, and can also use electrolytes equilibrated either with air or with CO2, again, for bio-related measurements. Now, the unique feature of the equipment that we have is that we integrated all these commercial microprobes from Unisense, which is pH, oxygen, hydrogen, or from Pyroscience, which is microprobe. We integrated them into our SVET equipment so that we can correlate position of the probe with its readings. And this is very important because otherwise, neither Unisense nor Pyroscience, at least to my knowledge, provides any means to correlate probe position with its signal. Now, there are a couple of examples that I want to share of the real work. So this is example that was collaborative work in the frame of WP code, big European project. And in this project, among with other tasks, we looked at lithium carbonate rich coating deposited on aluminum alloy 2024. And the results are now published also in this paper. You can take a look in more details. I will present what concerns local electrochemical methods here. So this work, and it was a collaboration, and so colleagues from AkzoNobel measured leaching of lithium from the coating. Then colleagues from TU Delft quantified corrosion inhibition effect. And the finite element model of this system was built by colleagues from VUB. And our task here was to validate model predictions with SVET measurements and also concentration of dissolved oxygen and pH in this case. So we worked with coated samples, either reference without lithium carbonate or the one containing lithium carbonate, and then the scribe of 1 millimeter to 100 micrometers deep. Very reproducibly, these scribes were produced by Airbus. So then this is a visual appearance, a schematic of the sample. This is a top view with the scribe inside and the side view. And we worked in freely evaporating electrolyte, and that's why the thickness of the electrolyte varied between 3 millimeters to 30 micrometers. And the volume was also very different. So in the scribe, the volume of electrolyte was 1 microliter. So we were able to run these measurements, in particular pH and oxygen, in very small volume of electrolyte. So then we also made a special cell for this measurement. This is SVET setup, but also for some pH and oxygen measurements, we simply restricted the volume of electrolyte by this glue, this hot glue. And so then the volume of electrolyte was very small to increase concentration of active inhibitor. And then we measured inside this scribe. So this is the first results. In this case, these are vertical profiles of oxygen and local pH recorded with microprobes, either for reference sample or for the one with corrosion inhibitor. And we started measurement 30 seconds after adding electrolyte to the system, so very, very soon at the beginning of immersion. And so for the reference sample, we observed a slight depletion of oxygen compared to the bulk values of oxygen, and slight alkalinization, again, compared to the initial bulk values. And for the inhibitor-containing sample, it was a very different situation. So within 30 seconds, we observed extremely high alkalinization, and this is due to fast inhibitor leaching that hydrolyzes and stabilizes pH at the value above 9.4. And 9.4 is well above pH stability range of aluminum hydroxide that is stable in the pH range between 4 and 8.5. So at this pH, we destabilized aluminum hydroxide, and this allowed for very efficient oxygen reduction. And you see the remaining concentration of oxygen at the interface was below 1 ppm. So very efficiently, oxygen was reduced by active aluminum surface. Then we continued with horizontal profiles inside the scribe. And we see that situation changes as we move from initial condition to 15 and 30 minutes, both for reference sample and for inhibitor-loaded sample. So for the reference sample, in this case, we observe decrease of oxygen concentration because now corrosion process is accelerating in the sample without corrosion inhibitor, and pH is growing due to oxygen reduction. In contrast, for the sample with corrosion inhibitor, the pH remains rather stable and very high, but we observe increasing concentration of oxygen due to slower kinetics of oxygen reduction. And this is because there is already a protective layer of aluminum lithium LDH that builds up in the scribe and prevents diffusion of oxygen to aluminum surface where then reduction takes place. Then we also performed a mapping for the reference sample, oxygen and pH, and for the inhibited sample, oxygen and pH. And then what I've done, I simply put all these mapping values in one plot by data point and concentration of either dissolved oxygen or pH. So orange values are oxygen, blue are pH. And then it's a better overview, a bit easier to see all the values at once. So then for inhibited sample, we see very stable pH value across entire map, while for reference sample, pH varied below 5 and above 8. So there are already events of local acidification, and this is due to outbreaks of anodic activity. And for oxygen concentration, indeed, we see very high concentration of oxygen remaining at aluminum interface in the scribe because oxygen reduction kinetics is slow due to the layer of inhibitors that builds aluminum lithium hydroxide. But for reference sample, we observe strong depletion of oxygen due to active corrosion process. Then we continued with SVET measurements for these samples. And in this case, we used, let's say, prototype. It's a new equipment that is being built by Technolabor company in Estonia, with strong contribution of Dr. Silva Kalip from University of Tartu. And they build a new equipment that is not commercially available just yet, but we hope that one day it will be. But in this case, this equipment is able first to capture the topography of the sample, and then we can follow with SVET mapping, follow the topography of the sample. So this green area, this is topography, and then blue, that's what we measured by SVET, yeah, including coating and also 200 micron deep scribe, keeping the constant distance between the sample and the probe. Now, this is the results as a reference sample of inhibitor-containing sample between 20 minutes to 8 hours. And okay, the absolute values, there is still some activity in the case of both samples, but what was really important for us to understand that we are dealing with highly electrochemically heterogeneous surface. Yeah, you see here these outbreaks of local activity, both in inhibited sample and also in the reference sample. This is very important to understand that these kind of events also need to be included in the model for the model to be able to reflect what we see adequately. Yeah. So then, in this case, the active node was introduced to the model by locally accelerated kinetics of anodic dissolution. And only in this case, we were able to have a very well matching values of local current density between the modeled by finite element modeling and actually SVET experimental data. While if active node is not taken into account, then we see very low activity predicted by model, and so introduction of this active node is indeed important. Now I have one more example, if I still have time, or well, I will try to go very quickly. This is about, again, PEO-treated magnesium, and this work is part of PhD thesis by Dr. Bahram Bahef-Nazari, who has very successfully defended and continues with us as a postdoc. So in this work, we used AZ21 magnesium alloy, and we tested a number of inhibitors that were pre-selected based on the previous screening. And initial testing was done on bare alloy by using weight loss method. And so this is a reference weight loss, and then corrosion inhibition efficiency could have been calculated. And then what was interesting that once we started doing the same measurements, but on PEO-treated magnesium and presence of all these inhibitors, we saw striking difference between some inhibitor performance, whether it was tested on blank magnesium or PEO-treated magnesium. And I especially would like to attract your attention to these two cases where diethyl phosphonate was used as corrosion inhibitor and 2,5-pyridine decarboxylate. So the inhibition efficiency of standalone magnesium was quite similar for these two compounds. But once we tested them on PEO-treated magnesium, we see a very, very strong difference. The diethyl phosphonate extended corrosion protection significantly, so this over 50 days of immersion, and you can read this success story in this publication from 2024. But we were also very much intrigued by adverse effect of pyridine decarboxylate on PEO-treated magnesium. It was really unexpected that it did not improve, but other way around, it significantly decreased protective abilities of PEO layer. And so we looked of why this might be happening, and with the help of electrochemical impedance spectroscopy, and also with SEM and calculations, thermodynamic calculations using hydromedusa, we proposed that magnesium forms soluble complexes with pyridine decarboxylate, and this leads to destabilization of PEO layer composed of magnesium phosphate and oxide. And this really then disrupts not only the porous layer, but also the barrier layer on PEO. And so then we thought, if it's so, and if indeed this barrier layer is disrupted, then we should be able to see strong oxygen reduction on this magnesium sample. And then the local measurements were performed, and we traced concentration of dissolved oxygen and dissolved hydrogen simultaneously. And indeed, in presence of pyridine decarboxylate, we see significant depletion of oxygen locally at sample interface, and also stronger hydrogen evolution, which means that pyridine decarboxylate indeed disturbed barrier properties of this PEO layer. And this was very important conclusions for us, because we realized that inhibition effects observed for bare alloy cannot be taken for granted for PEO-treated alloys, and the compatibility of PEO inhibitor need to be validated case by case. So with this, I'm through my slides. I would like to highlight that indeed it's microprobe techniques are extremely powerful and provide plenty of information about mechanistic details of corrosion processes. And what I would also say that it's really important to formulate the question to properly select the technique. So once the question is clear, then choosing the techniques becomes much easier. And of course, combining several different techniques, including integral electrochemistry, surface analysis, electron microscopy, is always an advantage. I leave this slide for the recording so that you can take a look at more recent and also previous publications where a lot is described about application of microprobe techniques for corrosion. And thank you very much for your attention. And also I would like to acknowledge all the colleagues who contributed to this work. Thank you.
Thank you, Sviatlana, for giving our comprehensive view. Are there questions? If you prefer, you can add your question in the chat or directly turn on the mic and ask Sviatlana, please. So I would have one. I know to operate these techniques, you should have a lot of technical expertise when it comes to local techniques. There has been any advances in terms of automatization of these experimental procedures, Sviatlana?
Oh, that's a good question. Yeah, of course, we are very much in favor of using automated testing, and we do this quite successfully. But so far, we are making steps towards automatization of weight loss measurements of electrochemical, global electrochemical measurements, image recognition, and so on, also automating analytical techniques. We have built robotic testing platform that is being operated at our institute for a year now. And we are acquiring the data much faster than before with these automated methods. However, we are not there yet with local electrochemistry. Yeah? So local electrochemistry remains case by case. And to be honest, at the moment, I don't see why would we use local electrochemistry in a faster manner, because these are the methods mostly for really point understanding of specific steps in corrosion mechanisms. So I think we keep them so far one by one, and this is mostly manual process.
Thank you for sharing that. Good to know. We do have some questions. Is it possible to use the probe under dynamic condition?
If you mean electrolytes, then yes, of course, and that's what we do almost always. So for both SVET measurements, but also for pH and oxygen measurements, hydrogen, yes, we circulate electrolyte with lower variable speed of between 0.2 to probably 5 milliliter per minute. This is possible, and the diffusion layer is not disturbed, well, at least not much by this, and it's always possible to establish the thickness of diffusion layer by making vertical approaches.
I'm sorry, we are on the top of the hour, but time for one last question. Is it possible to measure cathodic and anodic areas undergoing uniform corrosion?
Yes, for as long as corrosion is uniform, of course, and I think I had some examples there. So yeah, you can measure this both with SVET and with pH, for example. But the thing is that for most of the metals, the corrosion is not uniform. Yeah, so whenever it's alloy, it's always or very often microgalvanic corrosion, and then the areas of anodic and cathodic activities are located on the samples. But yes, of course, local techniques are for distinguishing between anodic and cathodic activities at rather high resolution.
Okay, thank you. Thank you for your great contribution. It's time to move on. I will share my screen.